I know I'm in the programming languages session, but now for something completely different. I'm going to actually talk about something that's not that programming languagey, although there's a little bit of a programming language flavor to it. So living dangerously here. So I want to talk about a system that we designed at Cornell called Charlotte, which basically came about because we were looking at the way that blockchains work and thinking about how could we we're interested really in the potential for blockchain-like systems to be a general platform for building secure, decentralized applications. And so we kind of reimagined what that would look like. And this is work with a number of people at Cornell, especially Isaac Sheff was the lead on this, but others, and my colleague, Robert Van Renesse, as well. So we sat back and said, what if we want to build a general abstraction for decentralized applications, cross-domain applications that involve interactions between people who don't fully trust each other. So the blockchain world kind of has an answer for this, which is that we should have a global consensus mechanism that is going to totally order things that happen. And then we can have smart contracts built on top of that that will give us the arbitrary application logic that we would like to have. So this is an appealing approach in many ways. And in fact, we've actually done some work on languages for smart contracts, which I'll allude to later. But I'm going to want to focus on an alternative, which is maybe what we should be doing is thinking about blockchains as general distributed data structures, as an instance of something more general, and then designing systems around something more general. And so the observation here is that, yes, total ordering is great. It's a very simplifying abstraction, but many applications don't actually need total ordering. So others have observed this, of course. If you have causally independent events, they don't need to be totally ordered. Another issue is that the blockchains are trying to provide some kind of one-size-fits-all guarantees of integrity and availability, and a very a strong guarantee, but not necessarily strong enough for everybody, and it's very expensive. You have fundamental scalability limits. So some people nonetheless don't want to use the blockchains to store information they care about because they don't consider it sufficiently trustworthy. Okay, so obviously these limitations have engendered a lot of work to try to make things fundamentally more efficient, like sharding chains and having side chains. And of course, people have explored building DAG structures for blockchains. So I guess we were viewing these as workarounds. We want to explore an approach that fundamentally doesn't have a global consensus step in it. And it allows you to have global consensus as part of your application if you want it, but not impose it as part of the fundamental structure. So this led us to design this system we called Charlotte. It's named after the eponymous character in Charlotte's Web. So we wanted to sort of reformulate blockchains as a general abstraction that can support these kinds of cross-domain applications, and not only support cross-domain applications, but make them interoperable and composable. So in our setting, some of these applications actually include blockchains. So we can build a version of, say, Bitcoin inside of Charlotte or on top of Charlotte. So it's kind of a proto-blockchain, if you will, something that's a lower level abstraction that you can build other things on top of. So the basic functionality that it's providing is not too surprising. It's a distributed, immutable data structure that is self-authenticating because you can have pointers between different blocks, and those pointers are represented using secure hashes. So we think of this as a block web, and we use the word web kind of to allude to the web that you all know. This is kind of like that. It's intended to be a low-level structure that you can build higher-level things on. It doesn't have global ordering baked into it, so the data structure is a directed acyclic graph. And because it doesn't have global ordering, there isn't an incentive to construct big blocks. So ideally, you build a data structure out of small blocks. So this can model things like blockchain, but there are a lot of other structures that people want to build that fit into this paradigm. So Git repositories or BitTorrent or various other things. So these are all applications you can build on top of Charlotte. Okay, so by building something as a DAG of blocks, you get some properties automatically. Like you can follow one block and you can find the rest of the data structure and believe that it's all the way that it was supposed to be. But that kind of basic Merkle hashing functionality doesn't give you everything that you want as a security property. So integrity is one property that we care about a lot. So what does integrity mean here? Well, integrity is more than just being able to verify that the structure you see is the one that you expected to get to. It's also about making sure that the structure that's being built is the correct structure. So in Charlotte, anybody can create a block and advertise it to people. So how do you know that the block that you're seeing is the right block? Is it the correct next block in the blockchain? Or more generally, you have this data structure. How do you know that a block belongs in the data structure? So there are various mechanisms like proof of work and proof of stake and other ideas for how to achieve this kind of integrity. Or consensus protocols are another example of mechanisms. Okay, so that's integrity. There's also another security property that we care about is availability. So classically there are three axes of security: confidentiality, integrity, and availability. We're not worrying so much about confidentiality in this project, but that's of course an interesting thing to think about. So availability, the problem here is how do you know that a block that you hear about, somebody hands you a reference to a block, it's a hash, how do you know that it's something you can actually get? And the conventional blockchain answer to this is you just replicate it to everybody. Everybody has a copy of the block. Now that's incredibly wasteful, right? That's a kind of quadratic scaling, which is not going to work for many systems. So the question is then, how do we get these integrity and availability properties that you don't get just from the fact that you're constructing this data structure out of hashes? So that's actually, I think, the interesting innovation in this project. We came up with this idea of having attestation, what we call attestations. So attestations are signed blocks that exist in the data structure to provide guarantees about integrity and availability of other blocks, including other attestation blocks. So the way that we think about these is that attestations may be signed. They may also include extra evidence that comes from various parties. And actually, if you look at existing distributed data structures, including blockchains, you can view the things that are put into those data structures as different forms of attestations already. And what we're trying to do here is kind of tease that out as a separate abstraction. So attestations you can think of as proofs of properties that hold that may hold water for a given observer. So we don't want it. So attestations are not intended to be universal proofs. You may not believe an attestation. The idea is you may trust some people. You as an observer may trust some people, and based on who the attestation came from and the evidence that's provided, you may then interpret that to guarantee some kinds of availability or integrity properties. And so we're not. Charlotte is not very non-prescriptive here. And so what we're trying to create here is a framework where we can decide who trusts what and what properties are being ensured from the perspective of different observers. So when you put blocks into Charlotte, you can think of in the picture here, we have a purple and a blue block that's pointing to the purple block. But in addition, we have some attestation blocks represented by the I and the A, which are talking about the integrity of the data that we're finding in the purple block and the availability of that block as well. Okay, so integrity attestations then, you can think of these as some kind of guarantee, if you believe them, that a block belongs in a data structure. So if you're trying to model, say, a conventional blockchain, it might be a statement like, this is block number 176 in this particular blockchain. And then it would have to come with some evidence that you believe. Availability attestations, you can think of as telling you where to find information. So an availability attestation is a guarantee that you can obtain this block if you want it. And the way that you prove that you can obtain the block is by saying where to get it. And that might be in many places. So you have to have some kind of description of where it belongs. And again, exactly how that is structured is application specific. And so then when you have a reference, like in the picture here, at the very top, you can see there's a little purple square representing a reference that is stored in the blue block. The reference itself then also can contain attestations that allow us to interpret how trustworthy that reference is with respect to integrity and availability. Okay, so these attestations then are generated by various servers that are part of the system. And we have two kinds of servers. There are what we call Fern servers. If you remember Charlotte's Web, Fern is the character who decides who lives or dies. So Fern servers generate integrity attestations. They decide which blocks belong in the data structure in some sense. So miners in a conventional proof of work system are serving the rule of Fern servers because they in some sense decide that what belongs in the blockchain. And if you have in general, if you have some kind of consensus protocol, then the consensus protocol participants are acting as Fern servers. So they're going to execute some kind of protocol or do some work, generate some evidence that decides what is the ordering and what is the structure of the data structure that we care about. And then we also have servers that are generating availability attestations. So we call those Wilbur servers. So they are going to make sure that information is actually stored and accessible. And so they issue availability attestations, and they also provide information on request. Okay, so this is all kind of a very general abstract layer that you can build on top of. And to explore the power of this, we built several applications that can actually coexist within Charlotte, and they can even be composed. So we've built various blockchains. We built Nakamoto-style blockchain, Bitcoin, but we also built Prism, and we also designed our own new consensus mechanism we called heterogeneous Paxos, which is a version of Paxos which is so heterogeneous that there's sort of three different dimensions you can be heterogeneous on in a consensus protocol, and we're heterogeneous on all of them. So everybody can kind of disagree about everything. And then we also built a high-performance timestamping mechanism. Timestamping is something you really like to have in this setting. You can kind of decide when things happened. But total ordering is really not necessary for timestamping. We rely on an entanglement property, where you can kind of build a web of things. And we also built a decentralized version control system, which kind of acts like Git. And then the other cool thing about this is you could build all these applications, but now they have a common way of talking about each other. You have references that they can interpret in general. So for example, we took the applications I described on the previous slide and built a thing we call Darchive, which stands for Disaggregated Archive. So it's a decentralized versioned document hosting service. And so it uses all those things, timestamping and Git and blockchain and so forth. And so this gives you a reliable document history, which I think is actually a really good thing these days. Like we have generative AI, we can't rely on things to be correct through the content. And so it has all of these things as component applications. Okay, we can also, blockchains are just applications in Charlotte. So we can just have the blockchains coexist and they can interoperate and they can point to each other. And we can have cross-chain references. We can even have blocks that exist on multiple chains. So if you want to commit atomically to multiple chains, you could do it if you have mutually understandable integrity attestations. So there's some room there for designing that. And for some kinds of integrity mechanisms, like quorum-based consensus, it's very easy to generate mutually understandable integrity attestations. It's sort of a natural extension, natural thing. Okay, so I'm running low on time, but a lot of the work actually was in figuring out what do attestations really mean and coming up with a general framework for interpreting attestations. So Charlotte does not prescribe a language of attestations. It's actually up to applications to decide how to interpret these things. Because fundamentally, you don't trust everybody in the system. So you're not going to believe any logical formula that they hand you. So we didn't want to try to commit to that. So instead what we did was we defined a way to interpret attestations using a semantics of possible universes. So different observers have different beliefs about what different attestations mean, and then we have a framework for expressing those beliefs. So we can define what a universe is in terms of sets of possible blocks that might exist in the world, possible partial orders over those existing blocks that capture temporal restrictions. So you need that to talk about things like finality in Bitcoin, and also the set of available blocks that you can find. And then attestations cause different observers to come up with different opinions about what those possible universes are. Now, the cool thing about this is that once you have this semantics, then you can compose attestations. You can say, if you see the following set of attestations, what does that mean? And that turns out to be just an intersection over these belief structures. We built a prototype implementation of this. In some sense, what Charlotte really is, in some sense, is a RPC spec. It's a specification for a bunch of things that Fern and Wilbur servers will participate in, and it's very non-prescriptive, as I said. But we built proof of concept servers, and including the implementations of the various things that I've mentioned, like Darkive. I don't have plots to show you about performance. We have actually a lot of plots, but they're kind of hard to interpret. What we've been able to show is that, as you might expect, if you have integrity mechanisms that are customized to the particular applications, they can be vastly cheaper than global consensus. And another nice thing that we've been able to show is that by having availability attestations that don't require global replication, we can significantly reduce the storage overhead and the communication overhead in the system. Okay, so Charlotte is an attempt to take conventional blockchains and break them down into these simpler kind of atomic components that we can then reason about. And I think the cool idea here is to have these explicit attestations that talk about integrity and availability and have a kind of semantic framework for reasoning about them. So it's an extensible architecture for building decentralized applications and allows actually interoperation of these applications. Okay, and I'll just mention very briefly, we also have been doing work on programming languages. So one thing we've been working on is a smart contract programming language, which is based on information flow and uses compile time enforcement of decentralized integrity policies. So this gives you a kind of compositional security even for multi-contract systems where you're kind of stitching together code and data from different parties, and it compiles to Solidity. But I don't have time to tell you more, so I'll stop here. Thank you.
Thank you so much. I'd love to.
First of all, this is very interesting. I'm curious about whether or not these kinds of new consensus protocols, like Ethereum's current ebb and flow consensus protocol, where you have different notions of integrity, is that something, a single application that has different notions of integrity in scope, or an application built on each?
Yeah, so I guess what we think of, what is an application? So in some sense, for us, what an application is an opinion about how integrity and availability should work. And so applications have defined some set of attestations that they want to use, and they're going to define some semantics for what those attestations mean. Attestations are actually tagged with some kind of unique identity that's based on a hash of something. And we have a framework for allowing applications to express what their attestations mean. It's not necessarily the end-all and be-all of such frameworks. And it would be interesting to extend that framework to include things like, for example, we don't have a way of talking about probability in our attestations currently, and that would be a natural direction to extend things in. Thanks.
Yeah, I guess maybe my question is a little similar. So let's say I want to implement total ordering, let's say Nakamoto consensus.
Yep.
So I want to make sure, let's say, as long as the transaction is embedded K blocks, like K deep in the blockchain, and the majority of the mining power is honest, then the probability that, the transaction will get overwritten will be, let's say, negligibly small in K.
Right.
So, I guess you mentioned that this doesn't support any probabilistic reasoning.
Not directly. So the way that we support that actually is with this component. Sorry, where was that? In the attestation semantics, we have this notion of the strict partial order, and that is actually the way that we can capture assumptions about the idea that if you embed something deeply enough in the data structure, that it becomes irrevocable. We actually, if you look at the paper, which is forthcoming in talks, then there's an analysis that we did of our implementation of PRISM, which does actually have it handles part of the analysis. In some sense, there's a piece of the analysis which is probabilistic, which needs to be factored out, that we don't directly support. So we kind of handle, if you go to the PRISM paper, there's the proof that they do can be kind of factored into two parts, and part of that reasoning we can do within the context of Charlotte. But there's another part which we don't handle directly, and I think it would be interesting to extend what we've done to support that, definitely.
So like for classical style consensus, let's say EFT style, like usually the consistency proof is like doesn't need to use randomness, right? These are like very simple proofs.
Yeah.
So I guess can you if I write a classical style consensus with total ordering in the Charlotte framework?
That we can do completely within the setting of Charlotte, yeah, and yeah. So the heterogeneous Paxos protocol that we designed is handled that way.
I see. Yeah, that sounds very cool. But can I ask you a more? So sometimes like for these classical consensus, like the liveness proof will rely on some probabilistic arguments. But I guess you are saying for that part you cannot. It's the liveness proof. Right?
So we make we have one of these. If you look at proofs of consensus protocols like Paxos, there's usually some assumption about eventually some complicated assumption if you try to make it as weak as possible about eventually seeing things that are eventually seeing messages that are sent, and so the heterogeneous Paxos has one of these very complicated assumptions that captures the idea that you will eventually hear messages from other participants in the consensus protocol.
These assumptions are like different for the asynchronous model and partially synchronous model, right? So
That's right.
In this framework, can you reason for like these different models? Like let's say partially synchronous model has a different underlying assumptions about the network. Like for instance, it assumes during a period of synchrony, there's like some bound on the network delay, but I don't know the bound ahead of time. But whereas in asynchrony, like there's just no bound, and we are talking about eventually it will like have availability.
Right. Yeah. So we're in it. So I wasn't going to talk about heterogeneous Paxos in detail, but it's done in the asynchronous model.
We have a break coming up right after this. You guys can keep
Yeah, I'm happy to chat about it more. But and there's an openness paper about that, which you can dig into the details on.
Okay. Okay. Well, so I'll keep the question quick. It's really neat work. I'm wondering whether you ever get into challenges with composing properties, from these smaller systems or these smaller attestations. For example, you mentioned
Yes.
atomic commits to multiple chains at once.
Yep.
Could that end in deadlock, for example?
That's an interesting question. I mean, the system is general enough that you can probably cause all bad things that you would expect to see in a distributed system happen. So we do have kind of a recipe for how to do these atomic commits, but it requires having, so attestations actually have subtypes, and in some sense you have to have a mutual subtype of the integrity attestations, which is basically a way of saying you have to have integrity attestations. So if you see here, we have two chains essentially, and the way that you commit is by getting an integrity attestation which combines the integrity of both chains, chain 1 and chain 2. So if you can construct those kinds of integrity attestations, which is relatively easy in a kind of quorum-based consensus system, not so easy in, say, a proof-of-work system, then because you kind of have to convince other chains about the work that you did in some sense, right? So,
Thank you.
Yeah.